Guys, in this video lesson we're going to take a look at light, the way that it reflects, and then we're going to look at how that light reflects pertaining to specific types of mirrors. So to start, we get what is known as the law of reflection. Now the law of reflection is the way that light is going to behave as it hits a surface and then leaves that same surface. We call the light that hits a surface the incident. We call light that then reflects the reflected ray. So note on the diagram here we have the incident ray of light coming in from the left and then the reflected ray leaving on the right hand side. What the law of reflection states is that the angle of incidence has to match the angle of reflection. And the way that we measure that is with what is known as the normal. So we notice our surface on the bottom. The normal is just an arbitrary line that is drawn perpendicular to the surface at the point where the incident ray makes contact and where the reflected ray leaves. Because where that light hits is then the same spot where it leaves. As a result of this, the incident angle has to match the reflected angle. Light, this works very, very well. In a practical sense, if you do a bounce pass with a basketball and you do your best not put spin on it, you're going to see the incident angle of the ball hitting the ground being equal to the reflected as it leaves the ground and heads off towards your teammate. Right? So any way that an object can go and hit a surface and then bounce off of it, we're going to see this law in play, especially if we don't have much spin on, say a golf ball, a tennis ball, a basketball, a softball, baseball, something like that. So for reflection, we have two different ways that light can reflect. It can reflect off of a diffuse surface and off of a specular surface. A diffuse surface is something that we deem as a rough surface, so no image forms. This is going to be like a painted table or carpeting or the drywall in your house, right? Something like that where if you look at the surface and you don't see yourself or you don't see something reflected similar to what you would in a mirror, right? If you can't look really close to it and actually see fine details, there's no image that's been formed. Is there a shadow? Yes. Shadow's different than an image. The reason why we don't get an image on a diffuse surface is because the normals themselves aren't parallel. When light comes into that surface, light's going to behave, it's going to be parallel to one another. But as it hits a rough surface, the law of reflection is still obeyed, but because that surface is bumpy, where it makes contact is going to then have the normals be tilted. So angle in still equals angle out, but now the incident rays themselves don't all have the same incident angle, which means they don't all have the same refracted angle. So suddenly that reflected light scatters in all directions, and because it's not a uniform reflection of light, we don't get an image. Now a specular surface, right, something that we get off a smooth surface and we will actually form an image. The reason why we get that image is because the parallel light that comes in makes contact with the surface, and because that surface is perfectly smooth, all of our normals are parallel with each other. Having parallel normals means that all of our incident angles will match all of our reflected angles, so the reflected rays will be parallel as well, which allows us to see an image. Now we get a bunch of image attributes, right? So light reflects. Well, what can it do? What kind of things can we see? Well, we can compare the image that we see back to the original object in terms of size, orientation, and type. And when we talk about the size of an image can either be smaller, same size, or larger than the original object. Those are really your three options. The orientation of that image, it can either be upright or it can be inverted, which is a fancy term for saying upside down. An example of the orientation piece here would be you look in some kind of a mirror and you see yourself upside down, or you see yourself right side up. And then type is the hardest one, I think. You either have a real image or a virtual image. We'll get to that in a moment. So when we start doing our comparisons, here's what we get. For size, we take our object, which is the white arrow, and then the image is either going to be smaller, same size, or bigger. Right? Those are your options. So the arrow on the The leftmost yellow arrow on the image one, that's the shortest arrow. The middle one is the same length. The height, they don't actually line up on the slide here. I apologize for that. But the heights of them are the same if you want to go ahead and count pixels. And then the one on the far right would be taller, right? So we get smaller, same size, larger. Orientation, upright or inverted. If the arrowhead is pointed up for the object, upright would have the image arrowhead pointed up. Inverted, arrowhead will be pointed down. And then for type, we get real or virtual here. Here we have the object again, upright arrow. If that image shows up in front of the mirror, it's going to be upside down, and we're going to call that real. If the image shows up behind the mirror, it's going to be upright, and we're going to call that virtual. Now, our difference between real and virtual images might be going, well, what are these? I've never heard of that. A real image is something that is actually produced with actual rays of light. So wherever there is light, if an image shows up, that's where it can be. Real images get projected. So you could shine some light, form a real image, and you could show that on a screen. So you could put a screen somewhere, that image will show up and you'll actually be able to see it. A virtual image, on the other hand, is formed by light that's not real, right? The light doesn't exist. So virtual images will always show up behind a mirror, whereas real images will always show up in front, right? Because light from a mirror is going to stay in front of it. The light doesn't ever get behind a mirror. As a result, virtual images are upright, but they can't be projected. We have three types of mirrors that we look at, right? First one is a plane mirror. This is just a regular flat mirror that's on your wall, right? Picture of a mirror on the wall in your bathroom. That's a plane mirror. It's flat, right? It's a rectangle. It could be an oval, right? It could be decorative. It could not be. It doesn't matter. If it is flat, if there's zero curvature to that mirror, that is a plane mirror. How the image shows up compared to the object, it's truly what you see is what you get. It is going to be identical to how you actually look, right? So if you look in the mirror and the mirror is your shoulders and up, the image will be shoulders and up. If you can see your whole body, the image will be the entire body. If you wave your right hand, this is where the mirrors get a little weird, right? The right side of the reflection won't wave. It'll end up being the left side because, again, it's just it's going to be that exact flip of where you are. If let's say you stand upside down, right? So you go head down, head's going to be down in the image, right? Those are the sorts of things that we see. So like the driver's side mirror, and in your car, right, the one on the driver's side, that's a plane mirror. The rear view mirror, that's a plane mirror, right? Flat mirror, no curvature. What you see is what you get in terms of size and distances as well. So let's say you're standing 5 feet away from the mirror. Your image appears 5 feet behind the mirror, given a total distance then of about 10 feet between you and your image. If you stand 2 feet from the mirror, the image will be 2 feet from the mirror. Total distance there is going to be 4 feet. Next type of mirror is convex. So convex is one of our two curved mirrors that we're going to look at, and this is when the reflective surface is on the outer part of the curve, as indicated by the diagram. We have our incident light coming in, and then the reflected light leaves. So the reflective surface is on the outside. Because it's curved, the curvature allows this to have a focus. For a convex mirror, that focus is behind the mirror. And because that focus is behind the mirror, that light that we get is going to attempt to converge behind the mirror where the light doesn't actually exist. This results in convex mirrors only producing images where objects appear smaller, they're always upright, and they're always virtual. So the image always seems like it's behind the mirror instead of in front, so you can't ever project these. Places where we see convex mirrors, the passenger side rear view mirror in your vehicle. It has a little tag that says objects in mirror are closer than they appear, because that mirror is slightly curved and you will always get that smaller appearance. If you look at a car in your rear view mirror on the passenger side, the cars look really, really small. Look at a car in your passenger side, that same car is going to look much bigger when it's the same distance away. Security mirrors are also where we see convex. So if you're ever walking around a store and you see up in a corner is usually where they are, a big curved mirror, that's going to be a convex mirror. It's going to help you see around corners. It's going to help keep you safe in case you're in a store at the wrong part of the night, or it's going to allow you to see, hey, is anybody coming down that aisle that I need to avoid? Like somebody is a forklift coming down there and I can't see it. Well, I probably shouldn't step in front of a forklift, right? So it allows that security piece to be utilized. Concave mirrors is the last type of mirror that we're going to look at here. Same idea as the curved mirror that was convex, but now the reflective surface is on the inside, which means the focal point where that light is going to go, and you can even see it on this diagram here, all of that light is going to focus towards the front of the mirror instead of behind the mirror. Because that's where the real light is going to focus, these can produce real images. So we can produce an image with real light. It's always going to be inverted when that happens. It's always going to appear upside down. Now, these don't just produce real images. If you are standing really far away from the mirror and you're well outside of that focal point, the image is going to be smaller, it is going to be inverted, and it's going to be real. As you get closer to the mirror, the object size will increase. When you get inside of the focal length, now you're going to produce a virtual image and it's going to be upright. So you're going to produce a real image that will be inverted when you're outside of the focal point. You will produce a virtual image that will be upright when you're inside of the focal point. Two great examples of this would be a cosmetic mirror. So if you take a cosmetic mirror, right, usually used for applying makeup or doing, fine, hey, you don't want to pluck that one hair in your eyebrow type deal, grab a cosmetic mirror, because when you hold it up, things look really, really, really big. Well, they look so big because you are inside of the focal length. When you're inside of the focal length, the image is larger. And because it's larger, you can really zoom in and see the fine details, which you may or may not want to see. Other applications of this, right, for the concave convex, if you take just a spoon, right, look at the spoon, look at the side that you would actually put food in, hold it arm's length away, and you're going to see yourself upside down. Slowly move that closer to your eye, and eventually your eye shows up really, really big. That's because you got inside of the focal length. Turn the spoon around so now it's curving towards you instead of away from you, right? Treat it like it's a convex. And then same deal, move it closer to you. You're always going to look smaller, upright, all the time. Solar cookers are another look at the concavity here. They are going to be built so that they focus light to a specific spot, and as that light gets that spot, it's going to cook your food. So that last look at concave and convex, again, just so you can kind of see a physical difference here. Concave on the left, that light is going to converge through that focus in front of the mirror. That's why when you're outside of that focal length, so on this diagram, you would be to the left of that focus, your image is going to be inverted and it's going to be smaller than the actual object itself, thus making it virtual. As you go inside of that focus, now that light isn't going to focus behind the object. Instead, it's going to focus behind the mirror, which is going to produce an upright image that is going to be big. Convex mirrors, because that focus is always behind, the reflected rays that come off of the mirror itself are going to reflect and they're going to scatter away. So what our eye does is it traces those reflected rays to the back side of the mirror, where we will always get a smaller virtual upright image, because that light is attempting to focus behind the mirror even though it's not actually there.